Thank you, Chairman, for the nice introduction, and good morning or good afternoon to all participants. I'm going to present to you a work with the title Development of a Concept to Achieve Lambda 1 for an High-Performance Spark Ignition Engine. But first of all, let me mention my co-authors, which are Mr. Alessandro Gallo, Mr. Matthias Spencer, and Mr. Klaus Fuß. The work is organized as following. I will start with a brief introduction containing the motivation of the work. I will then present the engine which has been used as base for the analysis. I will then speak about some technologies which has been investigated in this work. And in the next section, I will show two concepts which have been obtained bundling some of the investigated technologies. Finally, I will wrap up the main results into the conclusion. Let's start with the introduction. In the current production gasoline engine, enrichment is used to protect the component of the exhaust line from overheating. The most stringent limit so far was the temperature in front of the exhaust turbine, that we call T3, which was limited to 950 degrees Celsius. By the use of advanced turbine material, it is possible to increase this threshold to 1050 degrees, but the next limit becomes the temperature in front of the after treatment system, T4, which is currently limited to about 870 degrees. The goal of this work is to present a concept to be able to run the engine in the whole engine map in stoichiometric operating conditions. To do so, several technologies have been investigated by means of a predictive GT power model calibrated against experimental data of a reference engine. Let's introduce this engine then. The engine used as a reference for the analysis is a 4.4-liter turbocharged V8 engine recently developed by Porsche Engineering. The engine featured state-of-the-art technologies such as twin turbocharger, variable valve timing, and direct injection. The peculiarity of the engine is that the valve timing on both intake and exhaust cam are optimized individually for each cylinder. The engine is coupled with the hybrid powertrain and in particular to a 45 kilowatt electrical machine mounted in P2 position. The engine is able to provide 600 horsepower at 4800 rpm. This low engine speed, which makes it challenge to achieve such a high specific power, has been chosen to maximize the passenger comfort since the engine is installed on the state limousine of the Russian Federation. Currently, the engine is able to cope with Euro 6D emissions, and the goal of the analysis is to define a Lambda 1 concept. We set following targets. We want to avoid enrichment in the whole engine map. We want to keep the power and the torque of the current engine. We want to increase the system efficiency and reduce fuel consumption. And finally, we want to improve transient response. Basically, we want everything. In this slide, brake torque, power, specific fuel consumption, and lambda against engine speed are shown. The orange line represents the results of the GT power model calibrated against experimental data of the series production engine. As a first step, we modified the control strategy. We assumed either higher T3 threshold so that the lambda is limited by the T4, the temperature in front of the exhaust after treatment system. The high temperature turbine allows an improvement of 7 points of lambda at peak power, improving fuel consumption. Let's move now to the next section. In this section, some of the investigated technologies will be presented. The first step was the modification of the turbocharger. This is not really a new technology, it is rather a matching to the modified boundary conditions. For the Lambda 1 application, our supplier provided us with new maps for both compressor and turbine. The compressor diameter is increased from 56 to 58 millimeters, and the new design offers bigger potential towards a high compression ratio. The main changes are on the turbines.